here. Yeah, so you should see two browser windows open side by side. Can you confirm that you're seeing it? Somebody?
Yeah, we're seeing it.
Okay, cool. All right. So today's topic is basically overfitting and regularization. It's fairly, it's a fairly basic topic. I don't know why they put it so late in the thing, but in any case, let's look at it. And so I went through the class video. And I had a few notes. So one thing that I liked about the class, okay, before we go there, he talks about, the instructor, Alfredo. He talks about overfitting and, different kinds of fitting, right? So a model could underfit, right fit, or overfit. And I thought that this, this picture is actually a very nice indicator. So if you think of your data shaped like a parabola and you try to fit it with a straight line, then you're obviously underfitting. Fitting it with a parabolic polynomial would be the right thing to do, because your function is of the same power or the same order as your data. And overfitting is when you try to kind of microfit different points in the graph, right? So, and this is unlikely to actually generalize very well with other kinds or data which is out of this distribution, right? So so this was the basic idea behind underfitting, overfitting, right? And here, and he also mentioned, so I wanted to go back to this one. So a kind of a taxonomy of regularization techniques, which I thought was very cool. So he talks about parametric, functional, algorithmic, and indirect methods, right? So parametric is basically initializing weights with, basically weights initialization, right? Functional is L1 and L2 regularization. Algorithmic is, he's talked about early stopping and dropout. And then indirect, he talks about batch norm and data augmentation. Data augmentation I haven't covered. Every other thing I have covered in my, in these examples. So what I did with the examples was, if you remember from the lecture, they were all in one place, and he used to, open up comments and try to run it with a different kind of thing. So just, I basically unrolled it. This is similar to what I did with the autoencoders thing, the last session I led. Where he did the same kind of thing where he had commented out pieces and then he opened it up and then he, it became a new code. So essentially I have unrolled this thing, and few things he did not do or did not show. For instance, the early stopping, he did not show. And what else was there? I think he also glossed over the initializing weights. So things like that. So I basically, and also batch norm. So I basically added those pieces in just to, illustrate how they do, and also to illustrate for myself how to use it. Okay. So, so the point that he makes is that neural networks, by definition, are over parameterized, and therefore they are they run the risk of overfitting, right? Because they are so expressive. And so the idea is that you want to overfit the data, but then you want to regularize it so that it generalizes well, right? So it says the model is powerful enough to fit both the original data and the noise, right? So that's what we saw in the overfitting case. And so essentially, regularization is a way to reduce the power of your model, right? So make it, yeah. So overfitting for debugging, he makes this point, and that you take a small amount of data and you try to overfit your model. If your model doesn't overfit, there's a bug in your code, right? Or your model is badly designed, right? Or so basically the model is not correct, right? So that's the basic idea here. And okay, regularization being one of the ways. And then he talks about these initialization techniques. So he actually weight decay. Okay, all right. So he basically tells you what we, okay, initialization techniques. So the Xavier initialization is what he covered. So I can show you what I have, and we can talk about this. Before we go there, though, I would like to kind of go through the load data piece where he uses torch text. And torch text is kind of a strange package, which is like in massive amount of flux. So if you notice here, he says, if your version is 9.0 or above, you want to use the torch legacy because functionality has changed so much that it is impossible to use torch text, right? So, and that is true because even if you go down to this where you define the fields, such a, in the new torch text, this field object doesn't exist at all, right? So in any case, so this stuff is all simple, right? So it's basically setting a manual seed and then it's checking to see the device. And oh no, sorry, CUDA is available and it's setting the CUDA manual seed, right? Both the random seeds to some fixed value. And then he sets for the graphics, he sets these parameters for plotting. So it'll be dark. In my case, my background is white, but you'll see it's all dark. The pictures are dark. So you load the data, and you specify that your maximum length is 80. There is some amount of magic going on here, which is why I want to kind of cover this. This was actually kind of interesting. It offers a lot of functionality, I thought, but in a very badly packaged form. So you say datasets.download, right? So it will download the IMDb for you in your local area. And did I do this? I think I did. Okay. So it went to /, it goes into IMDb. So if you go to this, oh wait, what? Localhost, right? Yeah. Okay. So okay. So yeah. So you download the database and then you split it up into the train and testing set. And there you have to specify what kind of fields this data set contains. And that's where this comes in, the text and the label. And you say, okay, the path is here, and you basically download it. And at that point, you see that, it has 25,000 training data and 25,000 test data. Essentially, it's basically a negative or positive annotation and a movie review, right? So it says, okay, it's a positive sentiment versus negative sentiment. So it's a sentiment analysis kind of thing. And then further, once you get your train data, you split it further into train and valid using another random seed. So that gives you like a 70-20, I think. So this is test, it should say here. And so essentially, 17,500 and it just splits it up. And then you build the vocab here, right? And as you build the vocab, you have specified, remember, max length is 80, and you specified it in your field. So essentially, it truncates your field to the size of 80. Here is some magic, right? So this is interesting to know. And then, and you say, what is the max size? So what is the size of your vocabulary? So he has set it to 1,000 here. Initially, he had set it 25,000, but this is what the GitHub has. So it's a vocabulary of 1,000 words, and anything that is beyond, so beyond the top most frequent 1,000, any other word will be treated as unknown, UNC, right? UNC tags. So, and then basically he does that, and then, so, okay, so then he creates this vocabulary. Now, you can look at the most frequent, words in the vocabulary, tokens in the vocabulary. And then he also does, you can also do labels in the same way. And so you can see the text as like this, and also, and then, having the vocabulary automatically switches you in. So this text will be truncated to 80 tokens, and the just and about these tokens would be converted to their respective numbers. So it will become a sequence of 80 tokens, right? And if your movie review is less than 80, which is unlikely, but if it is, it should be padded, right? I don't think he has added the padding here, but I didn't do any changes here. So then you basically take, you just create data loaders out of this. He is using a bucket iterator with a batch size. I think it's 64. And he's saying that lambda x len so this is to sort the lengths of your data in or your sequences. I don't know why he would say x.text. Okay, so maybe so he's taking the inputs, the text inputs, and he's sorting them by size, and that way when you do batching, you will in each batch you will see text of the same size. So your padding, you can actually change the length, but I don't think it is relevant here because he's truncating it to max size, right? So in any case, so this is not what we are doing anyway. So this is just more or less to look at the thing. And then one thing, and now that you see output from the loader, right? So you can, so loader is basically an iterator. So this is the preferred way to do it, right? So you basically iterate through the train loader. So for batch in train loader, and you can keep going. The other way to do it, and this is the the basic iterator way to do it. And then once you look at it, now the test batch, as it comes out from the loader, it has changed to a sequence of numbers. So I think what has happened is, the presence of the vocab has created some kind of collating function that basically takes the text in the batch and creates sequence of ints based on the vocab, based on the vocab IDs, right? And so this is again, he does fixed batch generator. So here is another one where he says that bucket iterator returns a batch object, which, with dot text and dot label, but he basically wants it to return X and Y, right? Separate. So that's what he does. You could do it with a lambda as well, I guess. And so this is the final thing that you would get out of this, this fixed batch iterator, right? So, so first off, we do the baseline. We take his, the feedforward module that he's got. And this is just got, the input comes in as a sequence of ints. It is sent through an embedding layer with input size is input times embedding. So essentially what will happen is that, you take a sequence of a flat sequence of ints per record, and this will transform once it goes into the embedding layer, it will transform into a matrix of the size of the, the length of the input, so 80 say, and the size of the embedding. So it'll be, say, if it's say 300, then it will be 80 by 300. But here he's made a shortcut and he's made the embedding also 80, and we'll see how the shortcut works out later, right? So, and it's right here. So he's saying that, okay, I'll come to that. So, and then the output of the embedding is then sent through a linear layer. And then, oh, sorry. So this is just and it's got one embedding and two linear layers, right? So, and then if you look at the forward, so the input comes, gets embedded, and then it is flattened. And so remember that the embedding output is basically the max length of the input times the size of the embedding. Here, he has taken the input size and the embedding size to be the same, so 80 and 80. So therefore, he is able to do this, right? So ideally, it should have been input length times embedding dim, but then he would have had to specify the input size here, right? So which kind of got lazy, and he kind of did that. So in any case, this was something I was a little confused about initially. And then the output, so this is all flattened because a linear layer needs a flat vector to consume, right? So he basically reshapes it and then sends it through an embedding layer. The embedding layer takes the input, this flattened input embedding, and creates the hidden dim size of, again, a flat vector of size hidden. And then the output of that is sent through a ReLU, and which again goes through FC2, right? FC2 takes the hidden dim and converts it to, projects it to output dim, right? And then it's passed through a sigmoid and it's sent out. So here he's saying that the loss function he's going to use is BCE loss, which is good for binary classification, which is what we are doing, sentiment, right? The positive and negative. And so he says, like, if you are doing multi-class classification, then you would probably want to use a use a softmax, I think you should have said here. So he's just using a sigmoid, right? So So in any case, so then this is just setup stuff, so he's setting up the parameters, then he's instantiating the model, he's setting the device and setting the model to the device. He's defining the criterion, which is BCE loss. He's declaring the optimizer, which is Adam, and learning rate 1e minus 3. And this is basically, he just writes out the model, I think. Yeah, he's basically just showing the sizes. And so then you basically run the baseline. This is the training loop as it was in the original code, right? And so I'm not going to describe it. It's actually, maybe I should describe it. So so it goes through each epoch, and then as you take, you run through your train loader, get your batches, set your model to train, then extract your samples and labels from that. And I think he could have done that from here itself instead of doing that fixed generator. He could have just done use this, dot labels and dot text here, but whatever. And he sets the criterion. So he does the forward pass. He computes the loss, and then calculates the gradient of the loss, and moves the optimizers, updates the optimizer, right? The optimizer values, what's that called? Weights, right? Optimizer weights. And then every 100 iterations, he takes the training loss, and then he basically calculates the validation loss. He runs the model, so he switches the model to eval, and he runs the model on the validation set and computes the validation loss, and from which he computes the accuracy, and then he writes it out, the val loss, val accuracy, and so forth, right? And he appends to a history object, very similar to what Keras does automatically under the covers. And he's got these multiple history objects that he will use to create the graphs later on. And if the accuracy is the best accuracy, he creates the, at each stage he checks to see if the accuracy is improved. If the accuracy is improved, he writes out the model, right, on disk. And this is the output, as you can see here. And you can see that the training, on the training curve, the blue line is the train and the red line is the validation. So the model is, the training loss is coming down, but it is obviously overfitting beyond this point because, as you can see, the validation loss goes up, right before sometimes around 5, right? Yeah, it's kind of hard to see, but with the black. Anyway, and then he looks at the validation accuracy as well, and he sees it's kind of tapering off at this point. Right around the time, if you can see, this is, around the time where the loss the validation accuracy, this is loss graph, right? Yeah, okay. Right around the time where the validation loss starts to climb, this is where it starts to plateau as well, right? So it does limited accuracy beyond that point. So now, if we want to add the prior knowledge, this is basically the weights initialization. How would you do it? Essentially, all you're doing here is you're adding this block, right? So I have added another parameter to the constructor, initialize weights equals false, which is default to false. So, but if it's true, then it basically sets the Xavier uniform distribution to each of the embeddings and each of the linear layers, right? So essentially, instead of setting the weights of these things to random values, you're setting it to a known distribution. So basically what it does is that you're saying that I think the distribution should be this, right? So there are two of them. One is called Xavier and one is called Glorot, I think. In Keras, it was called Glorot. Here, I think it's called Who. Maybe, so anyway, so the documentation should say it. We can take a quick look, maybe. So torch and then init, right? Init. And calculate gain. So there is a uniform. You can set it to uniform. You can set it to normal. There is a constant, ones and zeros. Zeros is actually a bad one because if you set it to zeros, obviously you cannot, do any gradient calculations on it. There is Dirac, Xavier uniform is the one I've heard of before. Xavier normal is another one, right? Chiming, not who, sorry. Chiming uniform and chiming normal. So these are the two, chiming and Xavier are kind of popular. So so you can set it to here. Here, he basically talked about Xavier initialization. So that's what I did here. So now if you run the training loop, everything is unchanged, right? The only difference is that you have to set initialize weights equals true, and this will initialize the weights in your model as it's, when it's instantiated. And then even this is pretty much unchanged, right? This training loop. And you can see that the chart has now, it's steeper, right? So the training loss goes down faster. There is still, kind of a, it starts overfitting at around 5. And you can see that the validation accuracy, instead of going up, it has the loss function has basically changed, right? So that is the kind of thing that we did here. And then going back to our taxonomy, the other two things that we are thinking of, or we talked about, were the functional setups, which is L1 and L2, right? So two types of weight regularization. So essentially all it is basically, the parameters of your model. So the weights are, already set, right? Now you multiply the parameters of the model, multiply the weights of your model, right? And because of that, if you want to, you don't want any of your weights or any of your, any of your parameters to have a lot of influence on the model, right? Because then it can be susceptible to overfitting, because if you just remove that feature, then, suddenly the, model doesn't know what to do, right? Or if you change that feature a little bit, then the model, can move drastically towards something else. So that's the idea behind, squeezing down the parameters and, basically regularization. And essentially all it is, it's in the training loop. So here, we again, the network does not change, right? Initialization I have turned off from before, so I'm still using that one. But here, I'm taking, I'm creating the L1 norm. So I basically create the, find the parameters, right? So for FC1, the linear layer, and I also did for FC2, the linear layer. So originally the code that Alfredo had in his thing, he was only doing, computing the parameters from FC1 and then doing a norm of that, one norm, right? Here I've taken both FC1 and FC2, and I'm doing a one norm of both the FC1 parameters and the FC2 parameters, and multiplying it by a regularization constant, right? So this like beta, right? So if the learning rate is alpha, then this is the beta part. So and then I basically update the loss, and everything else is the same, right? So except that the loss function is now changed, right? And so essentially, and you can do the exact same thing for L2 regularization just by changing the norm here. So instead of doing, calling norm of, the FC, one norm of FC1 parameters and the one norm of FC2 parameters, you can call the two norm, right? So which is basically the root over the sum of squares. This is the absolute value of all these constants, right? That's what you, that's the sum of that. That's the one norm, and the root over the sum of squares is the two norm. And everything else is unchanged, and you basically get a slightly different curve. And you can see it's like a little different curve. I have a little graphic at the end comparing the performances. Not very deep, but it's there. But essentially, the idea is that the training parameters have changed, and therefore the training curves have also changed, right? The kind of training that it's got is changing. And okay, so L2, but however, there is, because L2 regularization is so popular, there is also another way to do it by setting an optimizer parameter, right, called weight decay. So here you're setting, so this is an alternative way of doing L2 regularization. So instead of putting the, actually calculating the loss function directly, you set the weight decay with the beta parameter, right? This is the value of the parameter that I want. It will automatically calculate the L1 loss, right? So again, it's it's all the same after that, and you can see that there is a different training curve and a different validation accuracy curve, right? So the next one he talked about is dropout. I actually mixed it a little bit. I forgot about dropout, so I did early stopping first, but we'll cover dropout as well, right? Or actually, I can maybe cover since so dropout is basically during training time. You turn off certain of the weights, and so essentially certain neurons. So essentially, when you forward prop and backward prop through it, it has no effect. It's as if the neurons basically disappeared from your network. And really what is happening here is that in effect, you are sending your input through, what may be in effect different networks, right? Slightly different networks. So there is the ensemble effect, like if you think of random forests where you take, your decision tree and then you take away or take pieces of the decision tree and then you create this big forest and you send your input through it and then ensemble your input at the end. It's kind of similar to that, right? So I'm just going to go and do the dropout first and come back to early stopping later, right? So here, what we have done is that, again, I have created a new parameter here. And so, I just set the dropout here. And if I detect a dropout, right? So I basically say how much dropout you want. 0 is the default, which means no dropout. But if I have dropout which is more than 0, then I will create a dropout layer. So essentially the output of the FC1 and then followed by the ReLU goes through a dropout before it hits FC2, right? And here I'm saying that, and the probability of dropout is given by the dropout percent, P. And I'm saying that use dropout only when I'm training, right? So I set self-training, which gives me true if I have model.train set to true, and model.eval if I set self.training will be set to false, right, automatically. So basically that's what I do here. Again, no change in the training loop. Training loop. This is again setting the parameters, and I basically just run through the training loop, and as you can see, again we have a different way of a different training curve. And then let's go back to weight decay. I think that's next here. Center variance. Oh, there is some other variance. So if you're using convolution networks, you can do, and with 2D objects like images, then you can do dropout 2D. And you can also do dropout 3D if you're using 3D inputs. And alpha dropout seems to be like dropout with batch norm kind of thing. So it also, as it does the dropout, it takes the remaining outputs from the dropout and then kind of smooths them down into like a mean zero standard deviation one, right? So it's like, almost like dropout plus batch norm. Okay, so the next one is early stopping. Early stopping is basically saying, if you look at this here, this is probably not such a great, well, I mean, okay. So if you see you see that in general, the trend for the training curve is going down, right? So as the number of epochs, as the model is trained for epoch over epoch, the training loss will keep going down, which is correct. However, the validation loss goes down and then starts going up again, right? So this signals kind of overfitting. So the idea here is that you detect this, right? You basically capture how much your validation loss was in the previous run, and then if it rises beyond a certain level, and you have rules there. You could say I want to do minimum 5 epochs before I decide to do this, because I want to give the model a chance to stabilize. So things like that. You basically say that if my validation loss is more than what my validation loss was before, previously, then I will break out of my training, right? So that is basically what early stopping is. So PyTorch Lightning, if you use, it has an early stopping checkpointing facility similar to Keras. In PyTorch, however, it's pretty easy to do. So essentially all it is you have this little so I added this block of code here, right? So it starts from here, ends here. So essentially it says that, calculate the val loss in NumPy, because I'm working in NumPy for the, the computation, the comparisons. And the first time it runs, the min val loss is null because, that's what I set it to. But if it's none, then you set it to whatever it is currently, and then you get out. And then you say, okay, if val loss is less than the previous minimum, then you basically say that, you set epochs no improve to 0. And otherwise you increase the counter to epochs no improve. So essentially, here the breakout, the early stopping condition is that the number of epochs must be greater than 5. So it has to have done 5 epochs of training. And it has not, the validation loss has not improved over the previous 5 epochs, right? Epochs, num epoch stop, right? Okay. So, and epochs no improve. So I think there is 6 is my, where is this? Here. So, so I do, okay, so here my epochs no improve, I have basically done only 1. So essentially that's, it basically looks at this condition. If the condition is satisfied, then early stop is true. And if early stop is true, it breaks out of the training loop, right? And you can see that, it tries this, and then it, as it flattens out, it basically stops, right? So that was the early stopping. And finally, batch norm, it was just, they talk about it here. And essentially batch norm is also, it's basically, at between each layer, there is this batch norm layer, which takes the distribution of the outputs and reduces it to a distribution with, mean 0 and standard deviation 1, right? And this kind of makes, it's, so it's kind of similar to the L1, L2 regularization in that it keeps the parameters kind of tight around this, close to 0. So here, and also in a certain way, it is also similar to dropout in the sense that, each time batch norm will create a different distribution at the end of each layer. So essentially, it's like sending, different kinds or multiple inputs through the same network, right? Slightly different network. And again, the ensembling effect kind of holds true here as well. So here, again, I've just made a very small change here. I said use batch norm, and then if I see use batch norm, I put in a batch norm between BN1 and BN2, right? So, okay. So I just created a single batch norm, BN1, which sits between FC1 and FC2, right? So, and if use batch norm is true, then basically add that in. And again, the training loop is unchanged, so, and you can see that there is a slightly different way, accuracy here. It seems that the accuracy is still rising here, so this is a good sign. And also, if you see that, sorry, it's the validation loss is kind of tracking the training loss as well, right? So if you do a summary, what I did was I took the validation accuracies at the end of the epoch at each stage and I plotted them. You can do other stuff because you have access to the histories. It turns out that the weight initialization did the best here, although I'm not sure what you can, draw from this, right? What conclusion you can draw from this. But it's basically different ways to do regularization illustrated with code. So that was it. Do we want to stop for questions? We can, if you questions or discussion points. Sorry, I kind of monopolized the whole thing. No.
The only comment, Sujit, is the one other thing I've seen referred to, although never directly applied. It's been just that it acts as a regularizer is a high learning rate as well, because it tends to help you not
I see. Okay.
stick to local minima.
Okay. Yeah. There is also another one. I don't know if we covered it. No, maybe not. Let me check. Learning rate scheduler, right? I don't know if we covered.
Yeah, and that's part of the whole thing with learning rate, which is the whole fast AI ecosystem is
Okay.
heavily focused on optimizing the learning rate and varying it across the various layers, maximizing it for particular things, and a whole lot of things that you can do with learning rate.
Right. The Leslie Smith approach, right? The triangular learning rate and everything. Okay, got it. Okay. Right. Yeah, that totally makes sense. Yeah. That's actually something, yeah, not covered here, I guess. Okay. So should I move to the next bit? We'll be done then pretty soon. Yes? Okay.
Yeah.
Yeah. So the next piece is okay, transfer learning. Oh, so before we actually move, so he also just like the other regularization effect is obviously more data, and that can be achieved through data augmentation, and there for images there are various built-in things. So you can compose them in PyTorch. You can take these transforms and compose them in like a sequence, a probabilistic sequence even. So center crop will basically take the image and focus on the center. Color jitter changes the color slightly. 5 crop, I think, does 5 types of crops. I'm not really sure what it does. Linear transformation does some kind of stretching, rotation, right? Random affine is again similar, no rotation though, I think, right? Random crop randomly crops your image. Random rotation rotates it. There is flip, horizontal, flip, vertical, right? So yeah, horizontal flip and vertical flip. Also, so I'm just going to digress a little bit for the clip stuff that Arto and a bunch of us did. And we use this to augment our images. And we also did text transformation, which is, which was really Gautam's contribution there, big contribution. So he basically did back translation, right? He took captions and he did back translation through the Merriam-MT family, right? So he would translate into, say, French and then bring it back to English, right? So, and the text would be slightly different, right? So that is another option that, a popular option that for text augmentation that maybe, it's something that we should know. And obviously so this is about data augmentation. And then there is the piece about fine tuning and transfer learning, right? So there are a bunch of models which are, really good at what they do. They have been trained on, massive amounts of data by third parties who have access to that data or the compute power for that data. And then they are made available to the, general computing public. And so what you can do is that maybe take a model that was trained on ImageNet to distinguish between 1,000 categories of things and use it for image classification for, say, medical images, right? So you want to say if this is a lung, X-ray of a lung or the X-ray of a kidney or something, right? So you would take that trained model and then with a low learning rate, you would fine-tune the weights with a smaller training set of, say medical images, right? Of whatever you want. Or some kind of other image data set that you have and which you are interested in classifying. So there are two flavors of this kind of thing. So one is transfer learning, where you basically just take the head out, the head of the the big trained model. So say for the ImageNet, it was trained to classify 1,000 kinds of things, right? Images. And so you basically chop that layer off, which does, it takes the output of the convolutions and basically does the 1,000, it's basically a linear layer and which does a softmax over 1,000. You chop those layers off and you replace it with layers that you are interested in, right? So maybe you have 10 classes of things that you care about. So you have a, a head which is just got 10 classes. So essentially, then you are using the trained model as a vectorizer. So you pass your images in, it creates the vectors, and then you take those and you have a network that basically classifies them to your classes. The other option is fine tuning, where you not only you are not freezing the pre-trained model, right? The layers of the freezing model. You essentially unfreeze it and allow, with a very low learning rate, you allow the weights to be updated, right? Or you allow parts of the weights to be updated. Maybe the last few layers to be weights to be updated. The rest of it you freeze. I haven't got examples here, but it's actually fairly easy to find. The only cool part is how you freeze the layers, right? So that's but those are the general strategies, right? So this is about the fine tuning. Oh, also, so he also talks about L1 and L2 regularization, and so we already talked about how it basically tries to push the parameters of the model towards zero, right? Sorry, the weights of the model towards zero. So they're very small, and changes in a feature does not affect the output of the model. Changes of a single feature does not affect the output of the model drastically, right? So essentially, if you see that if you draw a histogram of all the weights without regularization, so you will find it's kind of a normal distribution. However, with L1 and L2 regularization, you would find that they tend to the mean, like kind of a peaky mean kind of thing. And with L1, it's almost wholly concentrated towards the center. And whereas with L2, it does decrease, but very sharply, right? So that's what we, when people say that L1 regularization is sparse, that's what it means. That is like really, clustered around zero, and everything else is non-existent. And L2 is less so because of the little tail that it has, right? Yeah, most of the weights were non-zero. Okay, so that's basically it takes care of the entire thing here. And let's go to do Bayesian neural networks. This is different from Bayes networks or Bayesian networks. This is essentially talking about trying to figure out the uncertainty of predictions, right? So first off, what he does is basically creates a complex, noisy data set, right? And so this is a noisy data set that he's got, and he wants to create a neural network to fit this, right? So he asks you to do it with a tanh linear layer versus a ReLU layer, a nonlinearity, sorry. And so this is a simple sequential network with three layer networks, right? With dropout at each stage, and with tanh nonlinearity at each stage, right? So, and then you do a training loop. It's a tiny network, so it does it really fast. So you do it for 1,000 epochs, and then you basically plot the results, and you plot the y value, the predictions against that, right? So if you do that, you get something that is like really, it matches. It's again, the network is able to match it almost exactly. However, so this is what happens when you try to take the predictions with eval, right? However, if you do training, because of the dropout and because of the stochasticity introduced because of dropout, at each stage, it may be a slightly different p, you get results that are like this, right? So essentially what you're trying to do in, so this is like, you can see it's variable, right? So at this point, for instance, so if you look at somewhere here towards the corner, right, you see it's quite variable. But as it gets inside the curve, where it's more frequent or closer to the points that are already specified, it gets much more closer, right? So essentially, if you set it to train, and then you do multiple such prediction runs, you basically can draw a distribution around your the base prediction that you found, and how the width of this distribution. So essentially, all these you take maybe 1,000 times you run this network, And then you plot a histogram of, or you basically say, what is the standard deviation of this distribution that I have, right? At this point, I got so many values. What is the mean and the standard deviation? So here the red line, here the red point is the mean, and the standard deviation is given by the purple area, and you draw it for the entire thing. And you can see that near the places where the points are nicely specified, where a lot of points are specified, the uncertainty is less. Oh, the width can be thought of as the uncertainty of the model at each point, right? So as you go away from the distribution, out of distribution, your uncertainty increases, and as you are stay inside the distribution, your uncertainty decreases. So that's basically the message here. We can rerun this thing as he suggested using a ReLU. So Tanish does a better job of doing the fitting, but let's try it with ReLU and see what we get. It'll get more peaky, like more straight lines, which you kind of expect because ReLU has that here. So if you look at this thing, it tries to match it with kind of a bunch of straight lines, almost straight lines. And as you can see, as you go out of a distribution, the variance between the predictions becomes very large. And then you do the same thing. You draw the line with your mean and standard deviation for each point, and you get a different thing. So that's basically all I had. Bayesian neural networks notebook. Okay, yeah. Sorry.
In this case, he uses the dropout in the predictions too, right?
Yeah. That's
what I've seen done.
By definition, dropouts should not be there in predictions. Actually, although he doesn't actually give you that specification, right?
Because the way you get that variation is by actually for this particular, for predicting the uncertainty, my understanding from what I've seen elsewhere is you need, typically what you say is true, that you don't use dropout in the eval or, but when you're predicting uncertainty, then you use you retain the dropout in order to have the same dropped out networks. The variations of network predict the variations in your prediction.
Yes. So that's what he's done here. I mean, he's set it in train mode when he's creating these predictions, right? Right. So he's got this, y hat append XX view, right? So he's setting the net to train mode. So dropout is on, right? And then he's getting the output of whatever input he's given, right? He's passing it through the model. And then he's squeezing it and appending it, squeezing it into one dimensions, I think, and then appending it, actually squeezing it to remove the extra batch dimension and adding it to the y hat. And then he's taking the mean and standard deviation of y hat. So he's in train mode. So dropout is on. You're right. Yeah. I think that concludes today's presentation. Oh, wait, there is a, yeah, I have a, what? Oh, a stop share. Okay, never mind, sorry. There was a chat message somewhere. No, maybe not. Sorry. Okay, go back to Zoom. I'm going to start sharing again just in case folks want to. Actually, let me move this off before I do that. Yeah, I have multiple things open. So it likes to go to my first desktop, regardless of where I want it to go. So here, share. Okay, I'm back on this. Yeah, I'm pretty much done. So if you guys have questions, or we can discuss something if you want. there is actually another, so talking about regularization, there is something called regularization is all you need, just like attention is all you need. Yeah, there you go. So here, he talks about, okay. So this was, I thought we discussed this at an internal, paper reading thing at work. And this one is more for tabular data, and he compares with gradient boosted decision trees, right? So because that is the most popular method for tabular data. And then he basically says that if you have with adequate regularization, deep learning models can basically, perform better than gradient boosted methods. But usually gradient boosted trees are better. And so he talks about regularization cocktails, which I thought was pretty cool. So he takes multiple, but again, the focus here is more on gradient boosted trees. But he comes up with, so basically, the stuff that we learned here, he tries different combinations of those, right? And basically comes out with, here is, I think this is the output. But again, to some extent it is, and he comes up with different results. Oh, group cocktail. Yeah, so I don't know. I mean, I thought this might be interesting if you're very much into regularization, that, how do you, combine different regularization parameters to, experiment. So, even the approach that he's
specific, it by anything in the paper restricted to application to tabular data, or is it just that the comparison is with gradient boosted methods for tabular data, therefore,
yes,
but nothing inherently restricts the approach to tabular data?
No. It is basically because that was the data set he went with, or the data sets that he went with. And his interest was mainly to prove that, DL is better than gradient boosted methods under certain circumstances. So that was his hypothesis. I think it's further up somewhere.
Because at least in, again, in the fast AI world, they've always pointed out that the two approaches are gradient boosted decision trees, and you can get equivalent to actually better performance with basically deep learning models. There, the focus isn't so much on regularization as, you can get equivalent to even better than gradient boosted tree
I see.
performance. The difference somehow, though, is that, for most tabular use cases, there's also a desire to be explained, for the features and stuff to be explained, and that obviously falls out easier from a gradient boosted decision tree approach.
Right, makes sense. Yeah.
Than it does from a deep learning approach. So that is kind of the crux of the difference that the fast AI Jeremy points out. But otherwise, he says, you can get equivalent to better results with these.
Okay. Yeah. Cool. So anyway, should we give you guys back an hour of your life? If there are no questions, we can do that. Yeah. I don't, sure, you're welcome. Right. I have a little request. Let's see how many who are there. Actually, none of you are okay. So I guess this is kind of a basic thing, and we are reaching the end of the course as well. So participation is kind of slim, but it's okay. Yeah, I hope you guys liked what I presented. And
no, if you could also post the your unrolled notebook, that'd be great.
Yeah, I can do that. Yeah, I can do that. All right. So yeah, so I'll put a gist. I'll create a gist and put it up there as a public gist. because I don't have a fork of Alfredo's thing.
Yeah.
I'll just put it up there. Okay, cool. I can do that. And yeah, okay, all right. Then let's meet
Thanks a
next
lot.
week. Yeah, sure, absolutely. Yeah.
See you.
All right.
Bye.
All right, bye.